Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Hi, I'm Drew, and today we're diving into one of the most energetic phenomena in the universe, the collision of antimatter and matter. It sounds like science fiction, and for decades it was. But now, physicists are not only producing antimatter in labs, they're beginning to study how its explosive interactions with matter could unlock the most powerful energy source we've ever known. The collisions between antimatter and matter are the most efficient way to create energy that we have ever seen. And unlike fossil fuels or nuclear fission, this reaction produces no carbon emissions, no long-lasting radioactive waste, and no need for massive infrastructure. But is this just a distant dream? Or could antimatter someday help us power a clean, sustainable future? In this episode, we'll break down the science of antimatter and matter collisions, explain the physics behind their annihilation, and take a hard look at the challenges and potential of using this reaction as a next-generation energy source. To understand why antimatter is such a powerful energy source, we first need to understand what it actually is. Let's start with matter, the stuff that makes up everything we can see, touch, and measure. At its core, matter is made of atoms, which are built from protons, neutrons, and electrons. These are the subatomic particles, and they have special charges and masses. Protons are positively charged, electrons negatively charged, and neutrons are neutral. Antimatter is essentially the mirror image of regular matter. Every particle has an antimatter counterpart, called an antiparticle. These antiparticles have the same mass, spin, and other defining features, but opposite charge. For example, the antimatter version of the electron is called the positron. It has the same mass as an electron, but carries a positive charge rather than a negative one. This might sound like a gimmick, but antimatter isn't just an abstract idea. It was predicted in the 1920s by physicist Paul Dirac, who combined quantum physics, the study of subatomic particles, and Einstein's special relativity. Later, it was confirmed experimentally in 1932 when Carl Anderson discovered the positron in cosmic rays. Since then, other antiparticles have been created and studied in lab settings using high-energy particle accelerators. Here's where it gets fascinating. When a particle meets its antiparticle, they annihilate one another. The result isn't destruction in the traditional sense. Instead, their combined mass is converted entirely into energy. They aren't melted. That would leave behind a liquid. They aren't vaporized. That would leave behind a gas. They're just gone, turned into pure, massless energy. This is a rare process in our universe, but ironically, it's governed by one of the most famous equations in physics, E equals mc squared. That equation tells us that even tiny amounts of mass can produce enormous energy when converted directly, and antimatter is the most efficient way we know to do exactly that. But there's a catch. Antimatter doesn't naturally stick around. It is extraordinarily rare. In our universe, regular matter dominates, and on the rare occasion that antimatter appears, in high-energy cosmic rays, radioactive decay, or particle collisions, it's almost instantly destroyed through contact with nearby matter. Now that we know antimatter is the opposite of matter, and that their meeting causes the process of annihilation, it's time to get into what that actually means on a physical level. At the moment of contact, a particle and its corresponding antiparticle don't just disappear. Instead, their entire mass is converted into gamma rays. This isn't like burning coal or splitting atoms, where only a fraction of the mass becomes usable energy. This is total conversion. And again, it's governed by Einstein's equation E equals mc squared. In this formula, m is mass and c is the speed of light, which is simply an enormous number. Squaring that value turns even a tiny bit of mass into a massive release of energy. To put that into perspective, 1 gram of antimatter annihilating with another gram of matter would release roughly 90 terajoules of energy. It's about twice the energy of the Hiroshima bomb, from something that weighs less than a paperclip. No chemical reaction, no battery, and not even nuclear fission or fusion come close in terms of energy per unit mass. But this process isn't uniquely powerful by default. The energy released depends on how fast and in what conditions the particles meet. If you were to introduce antimatter gradually into a controlled environment, you could, in theory, harness that energy more like a continuous power source than a detonation, which would be the only way to actually use the energy. The challenge, of course, lies in control and containment. Antimatter is neutralized the moment it contacts normal matter. That means you can't store it in a metal pipe or box, because the container itself is made of matter. You can't even float it in the air, because air is matter. Instead, physicists use magnetic traps, vacuum-sealed chambers with powerful magnetic fields, to suspend antimatter particles midair, isolated from any physical materials. These techniques work for individual particles or even small clouds, but they're fragile and energy intensive. The longest antimatter has ever been held in a lab is only a few minutes, and even that required ultra-high vacuum conditions, extreme precision, and billions of dollars. Secondly, it is very difficult to obtain antimatter. In nature, antimatter forms fleetingly in high-energy environments. Cosmic rays, which is charged particles accelerated to near light speed by distant supernovae and black holes, slam into Earth's atmosphere, creating showers of secondary particles, including, on occasion, tiny amounts of antimatter, like positrons and antiprotons. Lightning storms also produce brief bursts of antimatter when particularly high-energy electrons emit gamma rays, which can spontaneously create electron-positron pairs. These natural sources are rare and transient, but they show antimatter is an intrinsic part of the universe. Artificially, antimatter production is a feat of advanced engineering and physics, requiring massive machines called particle accelerators. These accelerators, such as the Large Hadron Collider, propel particles, like protons, to within 1/1,000,000th of a percent of the speed of light and smash them into fixed targets or each other. These collisions release vast amounts of energy, very occasionally materializing into particle-antiparticle pairs. For example, a proton colliding at high energy can occasionally create antiprotons, positrons, and other antiparticles. However, this process is incredibly inefficient. Only 1 in a billion of these super-fast protons are able to be converted into usable matter, and the majority become ordinary particles or heat. The antimatter produced emerges amid a chaotic spray of particles traveling at various speeds and directions, making it very challenging to isolate. To capture antimatter, scientists use magnetic and electric fields to separate and trap antiparticles before they annihilate on contact with matter. Despite all of this effort, current facilities produce only minuscule amounts of antimatter at enormous financial and energy costs. In fact, we have only produced less than 1/10000000th of a gram of antimatter in almost 100 years since its experimental discovery. So, while the physics is incredibly elegant and theoretically powerful, the practical side of antimatter remains a massive engineering challenge. But that's exactly what makes it so fascinating. It sits at the frontier of both energy science and human imagination. The good news is that the extreme difficulty of harnessing this process is worth a lot in the long term. Eventually, we may have access to a sustainable energy source that is more efficient than anything in history. When we are looking for the ideal energy source, we're not just asking whether something works, we're asking whether it can succeed at working reliably, responsibly, and repeatedly. Fossil fuels work, but they pollute and deplete, meaning they aren't responsible. Solar and wind farms are responsible, and they work for probably the rest of human history, but they are intermittent. Night and solar patterns change effectiveness of solar energy, and wind speeds can slow down, making wind energy inefficient. Nuclear fission is another option, but it raises safety concerns, making it potentially irresponsible. Fortunately, antimatter annihilation could eventually check all 3 of these boxes. Let's start with energy to mass ratio. Antimatter-matter annihilation is by far the most efficient energy conversion process known. The theoretical efficiency is 100% mass-to-energy conversion. That means that minimal raw material is needed to produce the same energy output. From a sustainability perspective, this could drastically reduce mining, transportation, and storage burdens. If just a few milligrams of fuel could power a spacecraft or city, we could reimagine the entire energy infrastructure around compact, high-density nodes rather than sprawling grids. But to evaluate sustainability seriously, we need to look beyond output and examine inputs. How do we obtain antimatter in the first place? And can that process ever become energy positive or self-sustaining? Right now, producing antimatter is inefficient, costly, and deeply unsustainable. Facilities use particle accelerators powered by vast amounts of electricity just to produce a few antiparticles at a time. The process has a negative energy return on investment, meaning that it takes more energy to produce antimatter than we get back from it. That's a non-starter if our goal is clean energy production, and it makes the efficiency of the process irrelevant. However, this current limitation reflects the immaturity of the technology, not a permanent characteristic of the energy production method. It's worth noted that nuclear fission was once considered a fantasy, and solar panels were once prohibitively expensive. Both are now commercially available and used around the world, to the point where kids are able to make solar panel kits at home. Similarly, the monetary and energy cost of antimatter production could decrease if we make breakthroughs in accelerator efficiency, particle collection methods, or develop entirely new synthesis techniques. Another key piece is containment technology. Current magnetic traps that contain antimatter consume enormous amounts of energy and only work for microscopic quantities. A leap in low-power containment systems, perhaps involving different magnets or advances in the technology required to create and manipulate vacuums, would be essential for antimatter to become a scalable energy source. Such systems would need to store antimatter safely, release it in small, precise increments, and be resilient to catastrophic failure, since any contact with matter would destroy both the antimatter and whatever container holds it. In terms of environmental impact, antimatter offers a unique advantage. Unlike fossil fuels, it emits no greenhouse gases. Unlike fission, it leaves behind no radioactive waste. The primary byproducts of annihilation are gamma radiation and high-energy particles, which are dangerous bursts of electricity, similar to X-rays but stronger. In a well-controlled system, the environmental footprint would be negligible, an enormous improvement over any current energy source. There's also an interesting ethical angle to consider. Many sustainable energy solutions require massive land use, solar farms, hydroelectric dams, and massive wind turbine arrays. Antimatter, in contrast, offers extreme energy concentration in tiny physical space. That would reduce the need to displace ecosystems, flood valleys, or mine rare earth elements on a massive scale. Even more compelling is antimatter's potential as an off-world energy source. In deep space, sunlight is weak, and obviously there is no wind, and resupplying fuel from Earth is in many cases impractical. But antimatter, if generated efficiently at scale, could enable independent energy production systems on Mars, the Moon, or traveling spacecraft. These are not just science fiction ideas. NASA and other agencies have long considered antimatter propulsion as a candidate for long-distance missions because of its massive efficiency. Still, all of this is contingent on solving enormous technical hurdles. Antimatter's sustainability is currently theoretical because of the production bottleneck and containment energy costs vastly outweigh its benefits. But as with all evolving technologies, the key lies in sustained research, new materials, smart engineering, and cross-disciplinary breakthroughs in physics, materials science, and computing. The process of antimatter isn't that it will replace fossil fuels tomorrow. It's that it could one day enable an era where energy is ultra-dense, clean, compact, and accessible without destroying the planet in the process. So is it sustainable? No, not yet. But physics says it can be, and that possibility makes it worth watching. While antimatter sounds like something pulled from a Star Trek script, the global scientific community has been actively studying and working with it since its discovery in the 30s, not just as a curiosity, but as a tool. Although we're far from large-scale energy generation, real-world applications of antimatter already exist in small but significant ways. One of the most practical uses of antimatter today is in medical imaging, particularly in a technology called positron emission tomography, or PET scanning. In this method, a tiny amount of radioactive substance emits positrons inside the body. When these positrons encounter electrons, they annihilate and emit gamma rays, which are detected and turned into highly detailed 3D images of internal organs and tissues based on the strength of the gamma rays as they exit the body. This allows doctors to identify cancerous tumors and do something about them. The ability of PET scans to identify cancer is what makes it one of the only widely used applications of antimatter. On the experimental front, the European Council for Nuclear Research, or CERN, leads the world in antimatter research. In their labs, scientists create trap antihydrogen atoms, allowing them to study how antimatter behaves under gravity, how it interacts with photons, or light particles, and whether it obeys the same physical laws as normal matter. These experiments aren't about energy production yet. They're about answering fundamental questions like, Why does the universe appear to be made almost entirely of matter, with very little amounts of antimatter? These questions are still very important because of our very limited understanding of what antimatter really is. Looking forward, antimatter sits in a unique position, a blend of established physics and uncharted engineering. While practical applications are rare today, antimatter's theoretical ceiling is so high that researchers continue to pursue breakthroughs, even without short-term benefits. One promising avenue for these breakthroughs lies in next-generation particle production facilities. Current accelerators like the Large Hadron Collider were never designed for industrial-scale antimatter output. This means they will be much worse than those that will eventually be developed primarily for antimatter output. These new accelerators will be more efficient, higher output models, and are currently being developed. The most promising new type of accelerator is laser plasma accelerators, which use powerful lasers to smash tiny particles together and produce antimatter in bursts using less energy and smaller footprints than traditional particle accelerators. These designs may someday offer orders of magnitude improvement in production efficiency, an absolute requirement if antimatter is ever to power real-world systems. Meanwhile, advances in nanotechnology and cryogenic materials could lead to compact, lossless containment systems that don't just trap antiparticles, but would allow for controlled release, something today's traps just can't handle yet. This would transform antimatter from a laboratory novelty into a manageable component of energy devices, reactors, or even industrial tools. There's also growing interest in using antimatter to drive breakthroughs in other fields. For example, controlled annihilation reactions could one day provide a clean and precise way to initiate specific chemical reactions or produce rare isotopes currently very difficult to create. These applications would create breakthroughs in chemistry and biology. In effect, antimatter could become a kind of catalyst for other manufacturing processes, not just an energy source. Of course, these visions hinge on major advances in energy cost for the production of antimatter, ability to hold antimatter, and price minimization. But if even one of those bottlenecks breaks, it could create a domino effect across the entire antimetal prop line. The power of antimatter energy may not arrive quickly, but when it does, it won't just be another power source. It will redefine our entire relationship with energy, mass, and what it means to fuel the machines of tomorrow. That brings us to the end of today's journey, from particle annihilation to the promise of planet-saving power. Antimatter isn't just a concept confined to sci-fi. It's a real, measurable phenomenon at the bleeding edge of physics, and while it's not ready to light our homes or launch our industries just yet, it is a reminder of what's possible when we dare to push the limits of what we know. The idea that few atoms could one day power a city, or drive technology without pollution, fuel pipelines, or waste is more than just theoretical elegance. It's an invitation to keep asking big questions, to keep solving impossible problems, and to believe that the next breakthrough might come from the unlikeliest corners of science.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.